Today's Bob Pease Show is brought to you by Tektronix. Tektronix provides next-generation test and measurement solutions that can help you solve your toughest design challenges. With over 55 years of experience, Tektronix brings you the latest advancements in probes, oscilloscopes, logic analyzers, and signal sources, as well as application-specific software from Tektronix.
Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
This is the Bob Pease Show with comments on all this scope probe stuff anyhow with Bob Pease, which is me, and Paul Rako, who is over there somewhere, and Paul Grohe, who is over there somewhere. And we're going to introduce our guest of the day, Ken Price from Tektronix.
Okay, I got a little blurb about Ken right here. Ken Price is the marketing manager for Tektronix Measurement Accessories product line. He makes all the cool probes. Ken's been with Tektronix since 1994. Prior to that, he spent 14 years in market and engineering roles with Dranitz Technologies and Wang Laboratories. He attended Bucknell University and has 3 patents related to measurement and signal acquisition. Ken, come on in and let's learn about scope probes and Tektronix.
Thank you. Welcome to the place and the day. What are we going to talk about? We're going to talk about all kinds of scope probes. We're going to mention that in the good old days, a 1X scope probe looked like some coax cable that was fairly flexible, 3 feet, 6 feet long, and you had some picofarads, which slows your circuit down, and the whole circuit is barely good for 10 megahertz.
Is that picofarads per foot? Or?
Oh, it's 20 picofarads, at least 10 picofarads per foot.
Oh, God.
Yeah, it's pretty lousy.
6 feet and you're in trouble, right?
It's slow. Well, if you're looking at 10 hertz signals, nobody cares.
Audio probes. Okay for audio, right?
Well,
not even that?
Maybe.
Not even for audio. Right?
Certainly
No,
the golden
Not for
ears,
good high
folks.
frequency stuff.
A 10x probe looks more like the 9 megohms here, the 1 megohm back in the input of the scope. You got connectors and connectors, and you bring in your signal through the ground lead, which of course this is ground, this is ground, this is all ground except when it's not the same ground. And there's a capacitor you can adjust to get flat frequency response. No, up to 100 megahertz, it's maybe usable. Beyond that, you're really pushing your luck. You have to engineer anything past 50 megahertz.
The box is, that's in the adjustments right there?
Exactly. Can you hold that up pointing towards the camera? Can you grab that? That's the one you turn to adjust and tweak it. We'll discuss a little more of that later.
Put a square
Now,
wave there, right?
A good 10x passive probe can be pushed up to roughly 500 megahertz, but that's really the limit. Yeah.
Watch this.
And
That's a good ballpark.
Yeah, that's good ballpark.
Now, beware of off-brand scope probes, like the cheapest junk you can get, because as Mr. Rako points out, the circuit can cause rotten long tails, and you'll say, that was the lousiest cheap investment I ever made.
I saved $100, I thought, by using the off-brand.
And how much did you waste?
Oh, God, I'm troubleshooting for a week, a power supply design, and the waves are all drooping off. And why am I getting this droop? It was the lousy capacitors in the non-Tektronix probes. So now I buy Tektronix probes, even for home, right, for everything.
Time for a week is probably at least worth $100.
Well, 55 for, with the show.
Now, the problem with scope probes in general is that you can get a ground wire of 6 inches long, or you can rig it up for a foot, or 2 inches, or a half inch, or a quarter inch, or better. And the smaller is often better, especially if you're trying to do high frequency response.
Yes.
Always better.
You got
Always
your
better.
signal, you got a ground lead, you have noise. There's always some noise between the scope. Have you ever tried hanging a scope from silk threads? I've done that.
I put it on cardboard and cut the ground, probably shouldn't say this with Tektronix, cut the ground pin
Don't
off,
go there.
so float it, and then
even then-
you can't touch the metal, the old delay line. Don't touch that or
But
you get
even
killed.
then, the cardboard gives you strays and the 60 hertz coming in. Now, even a battery-powered scope has some problems.
Nah.
Not some.
Well, we're going
not
to talk
some-
about differential. The worst problem I had was thinking I was smart and doing the add-subtract on 2 probes, a dual channel, and then hooking them together like a poor man's differential probe and having this funny bump and a flyback. And I troubleshot that for a week until I did get the piece of cardboard out and float the scope and say, oh my God, that was a common mode problem in that off-brand scope I was using. Probably should have bought a tech scope back when I was poor too.
So part of the problem is the inductance causes frequency response problems in this loop, going back with the signal. And also, if you have any noise in the world, like if this is floating from anything bigger than 8 silk threads, you're going to have noise. And the noise will be pumped into this, which will cause voltage noise. The current is pumped into the inductance. It causes high frequency noise. And it's messy. We like to minimize that. And furthermore, when you have even worse problems, you get magnetic noise coupled into the ground lead, which makes rotten noise.
Yeah, you really got to watch that when you do switchers and other things with transients in there, especially televisions, switchers, anything that has a big sharp transient magnetic field.
Oh, because that just bombs in through the lead.
Yeah, it just couples in right through the lead.
Your big antenna.
How big is that loop? Oh, that's about 6 inches, 7 inches. Yeah. That's the kind where you get into trouble, and 2 inches shows a little improvement, and a half inches, well, better.
Paul showed me a great thing about taking a piece of bus wire to completely, you unscrew the top
Take that
here,
off.
unscrew
Take
that
that
part
off.
because you got a good
That
tech
helps.
probe that
Good.
disassembles.
That's
And take a piece of bus wire, wrap it around there.
We actually do make some accessories that'll
But those
do the
never
same
last.
thing for you. But you,
The way we use
lost
them.
all.
You always lose them.
Yeah.
So
Yeah.
a piece of 18 gauge bus wire, 20
Exactly.
gauge bus wire, wrap it around.
Here's one of those. So
Yeah,
That's
that's
cute.
the official one.
kind of like that.
Well, that's a
Yeah,
probe.
but
See,
we're
this is,
talking-
this is the
pretty good,
problem you
too.
run into.
As long as you've got the fundamental idea, you're
Uh-oh.
going
Yeah, it's
Well,
a
yeah,
different
different
brand
We'll
probe.
discuss that
But
later.
the bus wire, you can actually solder it down.
And you can
Stick
wrap
it
it
in.
real tight. I like
And
to
all
save
use
that thought. We'll talk later about
I
that.
like to use
great.
a half-watt resistor lead because it's very malleable and soft copper.
Yeah.
Right, right, and it springs and holds it.
Okay, now what Paul Rako a minute ago was talking about was setting up 2 probes to make a differential probe. Well, it sort of works, and it might work, but you're saying you get enough common mode, and it doesn't work very well.
Right,
It
and
does
you have
not
to
reject
invert.
noise.
We're amplifier
Oh, yeah,
guys.
we
Paul and
invert.
I work in the amplifier group, and you have to set one of those channels on invert. Something different's going to happen when that goes on. You've got to change the signal path. So now you don't have identical signal paths, and that's probably what put that little bump in that off-brand scope I was using.
And it gives you
Even
2
in a
channels.
good scope, but that's a problem. Trying to
this-
match the channels exactly is the
When you're
challenge.
inverting one. Now digitally you might be able to do that, right? But this was an old analog
Yeah,
scope.
but
This is
still
not a
problem.
great idea, anyhow. It's a conceptual idea which is not as good as it
Like
looks.
spice, huh? Conceptual, but not
So the
really.
first approach is to bring your scope probe out and, as he was saying, a 1/4 inch of wire. This is 0 inches, this is a 1/4 inch. You can ignore this horrible inductive piece of flexible wire, and you just bring this in as close as you can get. Now,
That's like with the little coil thing? Is that what
yeah,
that was?
similar.
Yeah, right.
Now, save all those little tiny parts that you almost threw away when you brought your scope, when you
all
brought your
this
probe.
stuff. This is
There are
gold
cute
right
little
here.
things that you shove the probe into, and it comes out with 2 tiny little prongs. That's good.
Guy.
Yeah.
That kind of guy.
And, or there are other ones that are a little bigger, but they're still very small in the area of volume. The inductance is very small. Now, one of my favorites, as Paul was discussing, is you take 20 gauge wire, such as 1/4 watt resistors lead, and you wrap it around this about 5 times. Then you tack solder it to a ground bus. And very close by you put some 22 gauge that I like to use, and you wrap that around the small spindle of the probe, and you shove the probe in there, and you wiggle it a little bit. It's very reliable. Other probe setups are not so good. You wiggle them, they get busted. This one is fairly flexible copper wire. You wiggle it, and it just sits there and holds on. And I don't have much trouble with this. And as it says, 1/8 of an inch spacing between this coil of wire and this hot signal, 1/8 of an inch between the ground and this loop of wire.
Yeah, what I like to do is, pardon my reach,
Go.
is use both ends of the coil. In other words, you'd come up, you'd wrap it around and come back down, and then you cut it at an angle. An angle like this. That way you can put solder
Both
down
ends.
to your ground plane,
right.
and the probe goes in at an angle. So
Dot,
you get
dot, dot, dot.
Oh, and that's all the one ground coil.
Yeah, it's all one ground coil.
So you got a short
That's
end on
good.
one side to get you close to the board, long end to tilt.
You ground it at both ends, and also you get an angle, so it's a little easier to go into the
Yeah,
circuit.
and so you still get the low inductance, and it lets you come in.
And these...
Because it's
these-
rare you can come in flat,
Yeah.
right? We
And
can
these-
design boards
These
for
little
that.
pins also fit those little machine socket, the IC sockets, the dip sockets has a little machine pin. If you can break one of those out of there, it perfectly fits on the tip of this, so you can solder that little pin to your circuit and make a
point.
nice
Another
little-
good way,
another
if you don't want to make a
nice
loop.
cheap scope socket.
Okay, good.
Good tips.
And the nice thing about that is
Pardon the
he
pun,
gives
yeah.
you 2 of them with every probe, but I can make 100 of these every time I need one. So once in a while, this is a very good idea.
Yeah, just wrap it around a resistor lead.
So if you have to build a board and you're positive it's going to work, you still have to use Murphy's Law for you. If you plan your testing and you plan your troubleshooting as part of your PC board layout, good. A, we warned you about it, and B, if you're prepared for trouble, trouble won't happen. Murphy's Law says if you are prepared for trouble, trouble will happen. If you're prepared for trouble, maybe it won't happen.
Maybe it won't.
Another way, for example, is if you have 2 signals, S1 and S2, they come along and you have a ground bus, which is really 3 ground buses to protect this from adjacent noise and noise. You can bring in 2 probes, or a probe and a pair, or a differential probe, and get your signal out of there without a lot of mess.
Now this goes back to your example about the differential measurements before, because more and more of the fast buses are going differential, they're going LVDS, and their traces are typically going to be configured like this, and you need to capture both sides, and sometimes one side to ground or the other side to ground.
Yeah, and keep that symmetry all the way
Need the
into your
symmetry,
piece
right.
of test
What I
equipment.
should have made then was this should be 0.1 inch at a 60-degree angle, so that you can
You go
probe
either
this
way.
or this or this or that.
Well, ideally,
Pretty
but
good.
the layout people are going to have something to say
Well,
about
we
that.
No,
have
they
to-
aren't. They're going to
yeah.
do what I tell them to do.
Right. We have to put our foot down that, mechanical engineers sometimes.
If you can get them
just-
to listen to you, that would be a great thing for me.
Right.
Fine.
But you have to do this in the layout. You got to beat on the layout people.
Yes.
I worked at a company where, the layout's a mechanical thing, so they had mechanical engineers doing layout. And they put the crystal here and the tank circuit down here because that made it arranged neat. And you said, no, you can't have an ECL oscillator with the parts spread all over. So now we have to provide for various testing, for various probing. That's all part of your design effort.
Exactly. It has to be engineered. It can't be left to luck, and it can't be left to layout when the guy doing the layout doesn't understand it.
That's why I do my own layouts.
Yeah.
So does Paul.
So here's an application. You could, for example, set up your PC board with a 450 ohm connector with SMAs going into a 50 ohm cable going into a 50 ohm scope. 450 ohms gives you your 10 to 1 attenuation, and these SMAs are pretty good at very high frequencies. We're talking about frequency. Frequency, schmequency, we're also talking about time domain. So some people really think in terms of frequency. We often think of terms of time domain, steps, settling.
Yeah, how much ringing, how much crap are you going to put on the signal?
Exactly.
This works remarkably good, but like Ken and I were saying, you got to have signal to burn. You got to be able to attenuate it by 10, and the loading can be low, but not as low as some of his FET probes.
You need a pretty robust driver to drive
Yeah,
that.
this is like for the laser driver. I'll show you over in the lab segment. I had, Paul taught me this. I had power to burn, and he showed me this setup, and it works pretty well. Not perfect, but it works darn well.
So you touched on something, Bob, that
Please.
I wanted to take further, and that was time domain or frequency domain. And if you're looking at steps, especially a lot of our customers are looking at digital signals, the frequency content of that, how fast that rise or fall time is really the important thing to translate back and forth. Because if you're going to really capture that transition, a clock transition or a data transition or whatever accurately, it really depends on how fast the rise time of that device is and the switching time, and what the equivalent frequency content of that step is to be able to
Right.
capture it with a fast enough probe.
So
do it accurately.
you're indicating that if there's a lump in there, you can't tell if that lump came from the scope, the probe, or from the signal. You have to calibrate things.
You have to calibrate
We
things,
agree on
and
that
you have
one.
to have the right tool for the job to begin
Yeah.
with.
And you need bandwidth. Paul and I were troubleshooting. A guy on the test floor had a problem. What was he doing? We had like three gigahertz probes, and it was a 1.9 gig signal. Is that?
It's a 1.9 gig signal, and we were off by 20%.
Just because of the roll-off of the probe. Because
Well, not just that,
Some of-
but the
well,
cable. He had a
yeah.
long cable.
Yeah.
A lot of it's in the setup.
Right, and you can cal that out, but you have to be aware of these issues. It's Heisenberg, right? The uncertain when you take information from something, you're going to affect it.
Right.
Yeah, good point. Now, when we talk about probes, especially old-fashioned 10x scope probes, you have to do the compensation by twisting this little screwdriver. Just hold that thing up, man. You hold that up and you say,
Where is it?
Oh, this one's
On
tricky.
the
It's on the
side.
side.
It's on the side.
And some
yeah.
of these you actually have to go under the label.
And if
And you don't
see,
use a steel screwdriver?
No, you don't use a regular screwdriver. You have to use the special insulated
a
screwdriver that comes with it.
nylon
Basically, or
Keep
Yeah, it's in
this,
there somewhere.
guard this with your, lock this in your desk. Don't leave it out on the bench. Kleptocracy, you'll lose it.
you can't use a conductive screwdriver.
Right, because that affects the
Use a piece of-
capacitance.
Well, use a piece of copper
yeah,
cut with a
You're
copper peel
adjusting
on
a
it.
small trimmer capacitor in there, so you can't have a big chunk
Metallic
of metal
thing
off the
in a
side.
grounded
You'll
case.
see it change as soon as you touch it. You'll see it. Oh.
So you cock it and then take the screwdriver out.
Trial and
it
error
comes
would
back.
work.
Yeah, you can use a regular screwdriver.
Who's got time these days? Time to market. So, okay, so you
So
got this.
you look at your scope and you put on a new probe that hasn't been used recently, and this is misadjusted, and you see this horrible overshoot or a horrible undershoot. You say, oh, I know what that is. And you tweak it, and it gets flat, presuming you have a flat calibrating waveform, and that's not too hard to get. You can usually find one of those
the older-
near or on a good scope.
The older scopes and some of the newer ones have the calibration routine, or have a tip on it where you put the scope probe on and
Right.
calibrate. But the thing is, you got to look at it, and it usually tells you which time per division range you have to turn it to get the right waveform to tweak the edge. Because if you go too fast and try to tweak it, it'll look like it isn't changing. If you go down too low, you won't see it, and it won't look like it's changing.
Right,
So-
and this overshoot, undershoot is the one case, the underdamped is the other, and everything looks slow, and it might not look as funny to you because it's just underdamped, and you'll take measurements, and you'll have a big crisis, and it turns out your signal's perfectly fine, you just haven't adjusted your probe.
Yep. Good point.
That's very good.
Okay. Now, as we were saying, okay, passive probes are good up to 10 or 50 or maybe 400 megahertz. But
Excellent.
above 200 to 500 megahertz, you probably want to get an active probe, which costs real money, but it may save you enough time and money that it's a good investment.
Worth every dollar you spend, believe me.
Because above 1,000 megahertz, you have to have a good active probe. You need it for precision. When you need high precision, you need the very good probe.
I'd like to interject, you need two of them so you can do arrival, you do delays. You need
Okay.
two identical probes to see how long was it in your circuit. When you have matched identical probes, tell the boss,
Okay,
you need repair.
why two active probes? Because of two items. Loading, if it loads your circuit, it'll screw up the circuit. And because of attenuation. An active probe does not give you horrible attenuation, and passive probes to do anything good at all are usually 10 to 1. So is this always true? Maybe not, but you really have to engineer what you're testing. You have to engineer it. You may have to have big enough signals. You might be able to live with attenuation, but you have to engineer everything when you're going that fast.
And the loading at these speeds, at gigahertz speeds
Oh,
that Paul was
picofarad is
talking
a
about,
pain.
is really critical these days because a probe is always going to extract some energy from the circuit. It's always going to have some impact and change the behavior. But when you're going gigahertz, the loading is a make or break proposition.
What's the impedance of 1 picofarad at a gigahertz?
It's a few ohms.
16 ohms
yeah,
or something? It's
A
not a
few
lot.
ohms. It's a
Few
lot
ohms.
more than you think.
Yeah.
At those
It's a lot
frequencies-
lower than you think, yeah.
Yeah, it's
160 ohms, Jay?
That,
100
that's,
yeah, after
Yeah.
you go out over
Okay.
100
100 and
megahertz
some.
on these, it's not the capacitance, or it's not the resistance that's killing you. That's why you don't see a lot of 100 mega or 10 mega ohm 1 picofarad scope probes, because
No,
at a
that's a
gigahertz,
DC.
it doesn't matter anymore because it's the capacitance that's loading your circuit. It's not the
Yeah.
1 mega ohm
and it
resistance.
doesn't take a lot of capacitance to kill a fast circuit.
Right.
Now, when you take a nice, fast, fairly clean square wave and you start looking closer and closer, and you expand it, what do you see? What's real? Is the waveform really doing that? Is it caused by the loading of the scope? Is it caused by the scope? Is it caused by your lousy signal source? Is it caused by the probe? What's real? Maybe you need 2 scope probes to figure out what's going on. Here was an application we had a while back. The guy had an LM339 type driving miscellaneous R's and C's of load, and it looked pretty good. He was using a 50 megahertz scope. He was getting a nice 3-volt step when the output fell. The only problem was, if you got a full bandwidth scope, 50 megahertz, 3 volts, 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 3 the output was being driven below ground to minus 40 volts for 1 nanosecond. And for a long time, these parts seem to be surviving this, although we're not sure. I think there was a Schottky in there, which may have protected them, but maybe the Schottkys got worse. And you get the output to minus 40 volts below the substrate. And some of these were failing 10% in a minute, 10% the next hour, 10% in the next day, 10% in the next week. It was really awful, and we finally got one in there with a full bandwidth scope.
You need a fast enough scope and probe.
And probe. And we had, well, this was big enough. You didn't really need a probe.
Actually, for this particular device, I remember this.
Yeah.
It was also, we had the problem of there was some high voltage involved. And because there was a transformer in it, we also got a lot of inductive kick. So we had to do a lot of these close, going in, staying away from all the high frequency circuits, going in directly, because we were also getting an inductive kick into the ground lead of the probe.
Ken, maybe you could explain this. This is real voodoo. I worked at Teledyne, high voltage switching power supplies. The scope probes, they take a big ferrite and they'd wrap a big chunk of ferrite here.
Right.
What are they trying to do? I never got what I considered an adequate explanation of what was going on by putting a shielded cable through a piece of ferrite.
Well, ferrite's going to limit some noise.
It's
just...
It'll make a balun?
Yeah, it'll make
Poor
somewhat
man's
of a balun, yeah.
So it just takes out some of the hash going back and forth in the
Right.
shield?
It makes a convenient point to wrap up your probe wire.
So that's keeping noise out of the shield side.
Well,
both.
it's keeping out of both, yeah.
Oh, because they'll
you got
both couple in,
conductors,
it'll take
they've got
common
both
mode out.
coupled.
Ah, okay.
Well, I have covered the preachy-teachy stuff, and Paul Rick, I believe you have something to read before we go over shortly to the workbench.
I sure do.
Good.
I want to read my microwaves and RF. We got a little thing. The lab segment's going to be sponsored by Penton today, Penton Publications. They publish this great magazine, Electronic Design, but they got this lunatic guy in here, this porridge guy. I don't know about that, but he's in here. Do you know this guy, Bob Pease?
No, that's my ugly brother. But
Another Penton is RF, microwaves and RF. What we're talking about, Brian Hallett talks about convergence, where at 90 nanometers it's all physics. Well, at these high speeds, it's getting into RF. You guys might want to subscribe to microwaves and RF because we're getting into RF concerns. You're getting into these kind of frequencies, just doing high-speed digital, just doing what's our new gigahertz buffer, 67?
6703, 04.
Yeah, gigahertz, IC,
gigahertz, double
integrated
gigahertz.
circuits, right? Amplifiers.
Absolutely RF. And we
Yeah.
see a lot of digital designers having to become RF, or at least signal
More
integrity
painful for them than for
experts,
us, yeah.
just to get the digital designs to work.
So Penton is going to be your friend with all this. They're going to teach you a lot of the principles. Like I say, all their magazines are good. I like, of course, Electronic Design because my pal Bob's in it. Electronic Design is a trusted information source for design engineers and engineering managers, delivering the latest news on key technologies, design, product, and professional information. Electronic Design readers stay up to date on all important aspects of engineering that impact design and technologies while offering competitive product advantages, including issues surrounding professional, legal, getting more important every day, career, and management matters. So let's go over to the lab, and we got a whole bunch of probes to talk about. We got some demos set up, and we'll get a little practice in with all this theory.
you're going to bring some of your chunk with you?
One little
Sure, I'll
ground
bring some
probe,
junk.
one
Sure.
little ground we want to bring.
You're going to bring ground all the way over there?
Yeah.
Isn't carrying a ground 10 feet?
I don't know, are we going to explain the berets?
Oh,
or just
yeah,
leave
yeah.
them under the
Hey,
radar screen?
You work for a cheap company, they don't give you berets. We got berets. What's wrong with you?
You're going to give me a beret? That's
There's
great!
one there.
We'll find one.
You leave the
one for my
scope.
scope.
You leave the scope. You can have the beret. It says customer first on your shirt, so
Yeah, it does.
we
Yeah.
could
We're your
use-
customer.
Okay, we'll talk.
We'll discuss it
We'll
later.
talk afterwards. Okay, so you want to
Okay,
get
let's
in here
go
first,
here.
right?
This is a LMH6533 laser driver. This is a little board I made. I wanted to give a little tout to my friends here at Proto Express who do overnight circuit boards when you need them, or really inexpensive 4-day boards. Ken Ball, he's a great guy, and he'll help you get your boards made. And part of all this high-speed stuff is you need real circuit boards. And we have milling machines here, and you can cut stuff with a mill, but when you get a real board, it's got a silk screen. Ken will put a silk screen on both sides for the same price. You can keep track of your components. You've got a solder mask. It just makes so much more sense to make a real board to test your high-frequency system because that's what it's going to end up on.
Tell them how much it costs.
How much it costs? What is it? $50 for a 4-layer board. You can get 2 4-layer boards for about $120, FedExed. So it's a great deal. We use them for these boards. We use them for all of our prototype boards. Here's the laser driver. If I'd have known Ken back in the old days, I wouldn't have put the chip so far. I was keeping all the inputs tight, being an old school kind of fellow. But really, the outputs are important. If you're trying to grab that half a nanosecond, this part has a rise time. The next rev of this board, which we've given all the customers, so I didn't have one to bring, the chip, Paul helped me with this, the chip's right here, so we minimize that output trace. But this does use that feature that Paul talked about, where this is the load. Maybe if I didn't short it out.
Ground.
Yeah, probably might short it out.
Short it.
This is a little resistor to simulate the laser diode. They're actually not dangerous. It's not a collimated thin beam that would make you blind, but we use a little resistor here. And then Paul's trick about using a 450 ohm resistor in series, as tight as you can get, because on the chip side of that 450 is where you're really concerned about loading. We're lucky here, the output impedance of this chip is incredibly low because it can do half nanosecond rise times. And then you can pipe it along on a controlled impedance trace all the way till you get to the SMA cable. And then here's the important principle, the scope has to have a 50 ohm setting. You got to put the scope on 50 ohms. And then you've got 450 on the board, 50 here, 500 total, 50, it's a 10-to-1 attenuator. And you can get pretty good. It's not as great as these fancy probes will do, but you can get pretty good and it's repeatable. So you can do changes and at least see the effect before you take a really precise measurement with a high-dollar FET probe.
Yeah, you have to remember that that's not calibrated and that the frequency response of that quote, probe will change depending on the length of the cable because of the capacitance on that resistor. So if you do that, you've got to be sure to use the same cable each time.
Repeatability, science, and that way your customers can repeat the experiment. Here's a little LVDS driver board. It's a DS90 LV047. The laser driver chip has LVDS inputs, which is really cool. It makes it fast. It works over a ribbon cable. But we had to make a little board that used one of our LVDS driver. It takes like a TTL style or a single-ended signal and then splits it into pairs. So there's 3 single-ended inputs here, and then you get pairs of outputs. So here you can put the fast pulse generator in. And what's interesting about laser drivers, this high-frequency signal is used to modulate the laser when you're reading. But when you do a right pulse, you have to turn that off, and you do the right pulse. The oscillator is free-running. They're not synchronous. So an older sampling scope that just builds the waveform with successive triggers, you can't use that. You need something nice like this beauty right here that can just grab gigahertz worth of data, grab it all in one shot and show you a picture of what you just acquired. And that way the asynchronous nature you can trigger on the rising edge of the pulse and then look and examine the sine wave because you've just caught it in one pass. You haven't built it up over time. Now Ken, why don't you come and show us, he's got a demo board in this high-dollar cool 6804.
Yeah, we have 2 scopes here actually. This is the TDS 3000 series that you were using earlier to probe here, and this is the latest, our 8 gigahertz scope to go with that 8 gigahertz differential
bandwidth or
probe.
Sampling
That's
rate?
Bandwidth.
8 gigahertz bandwidth.
Right.
Good Lord.
And
how
that's what it
fast does
takes to troubleshoot these fast buses these days. You've
And the
got
probes?
2, 3, 5 gigabit buses.
And the probes support 8 gigahertz?
The probes, this is the latest differential probe, and most of these signals are differential now. So we're really focusing on the differential probes at these speeds because it's Bob talked about grounding problems. Imagine your grounding problems at 8 gigahertz.
Exactly.
Right?
Well, that's what we had here, why we went differential on the laser driver.
Right.
Yeah.
So the demo I have here is not differential, but it's a little simpler, and it's just a signal board we have with a lot of different signals that we can use to demonstrate the scopes or the probes. In this case, it's just it's a square wave signal here, and you can see what we've got on the screen here. But if we look at a little faster time base here, we can see some details of that rising edge. And this is the kind of thing that's going to be of interest to someone trying to find out if they're going to pass their eye diagram, if they're going to pass their compliance test for rise time and for levels and settling time and all that.
Now this signal is coming through the coax?
This one's coming through the coax, and the nice thing about this is we can look at it very controlled 50 ohm path pretty good representation of what's here. But we have a probe point here, so we can also compare what the probe signal looks like to the very well-controlled 50 ohm path, right?
Do we have to turn that channel on here?
So yeah, we'll turn on channel 2, which is the probe, and we'll probe the same point here.
I saw it
I
wiggle.
think I need those
getting some
magnifying
action.
glasses we had out earlier.
There it is. You got it.
Okay?
Well, you've got
Beautiful.
And so we've got a
offset.
fairly short ground here and a very good representation of that step. And we're not measuring rise times here, but they would show up very, very close. But just for the heck of it, let's try a
Quick
little
question.
bit longer.
How does the delay compare? How long is the cable?
Oh, this one is like a 1.3 meter cable,
Yeah.
or 1 meter in some cases.
And the other one is?
The other one is a little over a meter.
Oh,
So
okay.
there is
That
some
makes
delay
enough
in there.
difference. Got
That's
it.
why they're offset like
Yeah,
that, right?
The offset correlates with the delay.
Right.
And I take it
Got
the
it.
scope itself will do like a 10 to 90% rise time measurement?
It'll do 10 to 90 or 20 to 80.
You
or
just
or
set it
you
up
can-
and
yeah,
it
you
gives
can
you the
customize
numbers.
it.
Oh, that's great.
Those two come up as automatic choices. So let's take that longer ground lead that Bob was talking about before. And this one's not even 6 inches. It's just maybe a
inches.
3-inch lead
Yeah.
right here. And let's try to probe. This is about a 200 picosecond step. And we'll try probing it
Oh, God, it's a
with
mess.
that ground lead
Look
hanging
at
out
this.
there.
It's
So,
all over the place.
Not only does it introduce that ringing that you were talking about, but look at all the noise it picks up from the other circuits and the other
Got
devices
it,
on the bench
yeah.
here. So it's just a kind of a rough illustration of the kinds of problems that we were talking about
Right.
before.
That 2 inches
right?
is not just a major pain. You just can't tell what's happening anymore.
No, not at these speeds.
Not at those speeds. Got it.
And so, 200 picoseconds, this is a 4 gigahertz probe,
Got it.
single-ended probe. It will accept all these convenient accessories, but depending on how fast your signal is, they may or may not be appropriate. So
Yeah.
we provide them for convenience when the situation will allow it, but you really have to be careful about how fast the signal you're looking at, how much you can load it down, etc.
Ah, okay. Now, could you show us, I thought this was cool, the way you carved out and put a bus bar underneath. Could we kind of
Oh,
Could you
zoom
comment
in
on
for
that?
clipping? That is
well,
a
these
cool
are just
thing.
kind of handy for bringing some signal points out. This one's ground here, which makes it real handy. This is the wrong
Yeah,
kind of
just get a
clip
regular
lead.
probe
but
like this, yeah.
Here, slide this paper underneath.
All
now.
right.
There you
Now you
go.
can see
Now
it.
we're fully functional.
So it makes it easy to hang on
Yeah.
either for ground or for, this is a clock signal here,
Yeah.
so if
This
we
is when
put
you can't
the,
afford a ground lead, if you don't have to have a really tight,
put the tip back on here.
that's a really clever way to have a nice distributed ground bus bar, and it's very low impedance. So the only problems you would have would be from the ground lead.
We've
on
actually
the
brought a
side.
number of the different signals out to these too, so it's not a bus bar all the way along.
Oh, I see. So you're bringing
So-
signal and ground.
Yeah.
Oh, that's beautiful.
And you can do that, if they're relatively slow. A lot faster signals, you wouldn't be able to put that much of a stub on the end and still have the circuit operate.
Right, right. At the
So-
speeds we're going these days.
So it's nice when you can clip on like this and keep the probe reliably attached. When you don't have the convenience of these things, sometimes it's a real challenge to try and hold probes handheld on these very small points. And for that reason, we've gone some of our latest probes to really purpose designing them to be soldered in place. And I've got these adapters here, just to give you an example. Some of the things that we have. This newest probe, the 8 gigahertz one that I talked about.
Hold on,
baby.
listen, so you don't
Thank you. Yeah, it's shown in a handheld configuration here, and you can change the pitch of the tip here. But this is really an add-on device so that you can use it handheld. The probe's really made to be used either as a handheld probe or, more commonly these days, you clip on these, we call these our tip clip adapters.
Okay,
They
hold
just
that.
clip on the end of the probe,
Hold
and
that
now
real
you've got,
steady.
yeah,
Let the
I don't know how
camera-
steady I can hold these
Let the
resistors.
camera get it.
But they're
testing
made
the
for
skills
soldering
of-
down, to solder down to a test point where you need to stay connected for some period of time.
So
with
that little
maybe,
piece stays with your board.
it can stay with the board, exactly.
I see.
And we ship a bunch of these, more than 2, Bob,
That's
with the
nice.
probe. Here, maybe if I'm not holding it, it'll be steadier here. But solder down, some of these test points are so small, so tightly packed, and more, board real estate is very
Killer.
scarce. And especially on the back of a BGA, for instance, you might have a pitch of 30 mils between adjacent test points. Trying to hold them on there with your hands for multiple
Yeah.
probes is just
Well,
about impossible.
The laser driver project to get from the baseboard in a DVD writer up to the optical power unit that shuttles back and forth, it's 0.5 millimeter pitch ribbon cable. And it's single-sided. They can't bring a ground plane up, so impedances are critical.
Yep.
And with that baby, if you could leave a couple of those, that would be great, because that would have solved
I'll be
my
happy
problems.
to leave you several tip clips.
Oh, those are great. Those
The
are
probe
great.
I have to take back with me.
I
now,
understand.
sorry.
8 gigahertz is...
I have my hands on it. Position is 9/10. Okay, put down your knife. You can have it.
Now, I take it's intelligent. When you plug that in, the scope knows it's got that probe
Oh,
attached.
good question.
And
Yeah, in fact, we had to engineer a new interface here using a version of SMA technology. The BNC that you may be more used to really runs out of steam at about between 3 and 4 gigahertz.
about 3 and 4, yeah.
So as we get higher and higher bandwidths, we had to go to a more reliable 50 ohm connection and also a more intelligent connection so that the probe can communicate with the scope. So it can tell the scope what its properties are, what its parameters are, even in some
my God,
cases.
that's great.
What kind of voltages it needs, because we've got, in this case, a silicon germanium differential amplifier down here in the probe head.
Mm-hmm.
So with their powered devices, they need DC power supplies from the scope and so forth. So there's a lot of intelligence going back and forth these days between the scope and the probe, and they really are designed as a system.
I see. Is there a power supply separate for that probe so I can go into my Tektronix spectrum analyzer? Have you gotten that?
For the
Is
older
that
probes,
useful?
for the older active probes that are BNC based, we have a power supply because they can stand alone
Right.
more. These, because there's so much interaction between the probe and the scope, that really depends on the intelligence.
You wouldn't be able to get the 8 gigahertz across
can't-
into a spectrum analyzer.
You can't really get, well, we do have, for the sampling scopes actually, we have a power supply that will adapt this, but again, we're trading information back and forth. The scopes have to have software to support the probe so that they can work as a system together,
I
a
see.
calibrated system. And there are things like range settings. This one has a range button that will select attenuation, so if you have a really small signal swing, a few millivolts, you can set this in a very sensitive setting, but it's actually the scope changing settings in the probe, even though the button's on the probe. So a
good.
lot of interaction and intelligent
That's great.
system calibration between the two devices.
And if you do want a conventional BNC or SMA, you just pop this little adapter in and off you go.
Yeah, whichever type you need, they just, they adapt to, we have one for even end connectors.
Oh, really?
So, yeah. So whatever you need to bring in 50 ohms, you're covered.
Now, does this, I take it at these speeds you can't have a mega ohm. Is there a high impedance setting for this, or is it everything's 50 ohms?
These scopes at roughly 2.5 gigahertz and up are all 50 ohm inputs. However, we do have a buffer amplifier that will allow you to connect a passive probe. So if you need to probe 12 volt power supplies or something
Right,
like
audio.
that, you can bring it in. But it's an external, it actually looks a little bit like this one. It's an external
see.
device that plugs in and gives you the buffer
So if you want
amplifier.
high impedance for whatever reason, you can get it.
Can adapt to it,
Oh,
yeah.
this is a great thing. Well, that's great. Anything else you want to bring up?
Thanks for the forum here.
Oh,
I'm
this is
glad to be
we
able to
love
talk to you.
Tektronix. You know, we love the
Oh, yeah.
Tektronix people coming down. I wanted to show, Ken brought this stuff, and it's good stuff, but the first things that came in our lab, here's a current probe that we got fairly recently. It's, Tektronix current probe, so it comes, there's the probe, as Alan Martin taught us about last show. And then you come out of here into a BNC connector, and you can do AC and DC current. It's really fabulous. And then one of my favorites, from being an auto business guy and you had to do spark plugs, you've got your high frequency probe. The older ones were filled with Freon, or I'm sorry, high voltage. The older ones were filled with Freon. Now that that's a controlled substance, they talked me into this one and saying, hey, pay a little more money, and then this one you'll never have to worry about Freon anymore.
Can't use Freon.
And what is it, I think 40 kilovolts.
Yeah,
It's
40
a-
kVp. It's
40
a
kVp.
silicone dielectric in there now.
Yeah, 1,000 to 1 and 3 picofarads, which is a lot for high frequencies, but for a spark plug signal, that's great. And then we have, this is one of your older ones. Like Metcal, we really use this stuff. It's not like they have to convince us. This is a 1 gig differential,
Yeah,
a
it's one of the earlier
6247.
differential
Is this still in production?
Absolutely, still in production. Yeah, and it's still, at 1 gigahertz, it's still used for a lot of applications. Very popular.
And this is a probe where you can get the little extra power supply if you want to put it into a spectrum analyzer.
Exactly, a BNC-based interface and the power supplies that the probe needs.
Okay,
from across
differential
there.
input. Here we have gold. I hate to tell people to hoard stuff, but if there's one thing you might want to put in your desk drawer under lock and key, it's this stuff, because they always seem to go away. But you can call Ken, and
Yeah, we'll sell you more.
He'll sell you more. Do you sell online on your website, or should we go through distributors?
We go through a whole lot of different distributors worldwide,
Yeah.
and they do a better job of giving instant delivery and service
Yeah, I believe
to our
Newark
customers.
Distributes
Lots
some
of them,
stuff.
yep.
We have Ariba working with Newark, so that's
Yeah,
always
but the
great.
information, the links are on our website.
And the wood box, right?
Oh, yeah. You guys
Yeah, we don't ship it in this anymore.
You ship it in
No,
a
the
plastic
it's a
box.
rainforest
That's okay.
bag.
So to keep the rainforest from being
Right.
damaged. There's a couple other things we wanted to bring up. We had this beautiful prop made, and we want to use it. So we're going to set this
well, yeah.
down, and we're going to try to show you how small, if we can get a nice stable area here, how small
Some of these devices,
some of these
that we're talking
devices
about.
are.
So
Bring
this
the
is one
cameras
of the
in.
this is one of the handheld differential probes, and
We'll
then
put it by
there's the
that
solder
time.
down version here. So you can see, and this is
Standard probe.
yeah, some of your standard probe. Really trying to meet the more and more challenging fine pitch devices that
What's the pitch on?
our customers need to access. These are 1/10 inch. There's an adapter that will give you variable spacing, so you can adapt to a wider range of spacings.
And that
of course,
pair
the
of wires?
resistors will go, any kind of differential pair that are running at these speeds is going to be within that.
And those fine wires are 8 mils or something?
Yeah, on the ends of these resistors, we have some different lengths of flex here for getting into harder to reach places. We've got also some larger 1/8 watt resistors. If you have a larger test point, they're a little easier to solder sometimes.
Okay, great.
I'm impressed.
The one other thing is I saw a glass case, and I thought somebody left their eyeglasses. Tell us about this, a standard accessory when you get a probe? Or
This is a standard accessory with the solder down probe here, because
this
some
probe.
people like me whose eyes aren't as young as they used to be. Paul, you wanted to try these on, didn't you?
Oh, man. The
Yeah.
beret, it works.
Sometimes you need a little optical
Next time
help.
we go downtown San Jose dancing, that's going to be the approved solution. And that's why I brought our beautiful Motec scope, the Luxo light with the little add-on, a few dollars extra for the magnifier. Seeing the stuff. You can't do the work anymore. You can't do the probing if you can't see it. So all of this is part of a modern lab these days. Tell the boss, sign the requisitions, and get you the things you need. Get you the Tektronix probe so you don't affect your signals. Get you the stuff so you can see what you're doing.
And save time and money, because you can waste a lot of time and money if you don't have the right equipment. It's
Boy.
amazing how a week goes away. Oh.
The mythical week. Anything else you want to bring up?
I just want to thank you for bringing us down and giving us an opportunity to talk about what we do best.
Okay, thank you. Bye.
Thank you.
Paul.
You sure showed us a good demonstration of what we need to get our job done.
Yeah.
Thank you.
Thanks very much, Bob.
Okay, thanks, folks.